In this lecture, we'll offer an intuitive introduction into the basic ideas that underlie the seminal branch of number theory known as algebraic geometry. Our introduction will revolve around a geometric argument that will allow us to identify all the Pythagorean triples. This geometric method will involve intersecting the unit circle with a certain collection of lines. These points of intersection will give way to the Pythagorean triples we seek. Of course, along the way, we'll take some time to review the basic principles and properties of lines and circles in the plane. These deep ideas linking algebra and geometry can be traced back to the ancient Greeks and are connected to the notion of conic sections, the geometric shapes created by slicing an ice cream cone-like surface with a plane. These subtle shapes, including circles, ellipses, parabolas, and hyperbolas, all can be described by certain quadratic equations. The fact that we can study these objects both geometrically and algebraically forms the foundation for algebraic geometry. Well, let's recall that a Pythagorean triple is a triple of natural numbers that corresponds to the lengths of a right triangle. For example, 3, 4, 5 and 5, 12, 13 are each examples of Pythagorean triples, as we saw in the previous lecture. Suppose that xyz is some Pythagorean triple. Then we know that not only are these three values natural numbers, but they are also a solution to the Diophantine equation x squared plus y squared equals z squared. They satisfy the Pythagorean theorem. Well, now, since z is not equal to 0, because z, after all, is a natural number, we could actually divide both sides by z squared. And if we do this, we would see on the left x squared over z squared plus y squared over z squared, and then on the right, this would equal a z squared over z squared, which is just 1. Now, x squared over z squared could be rewritten as just x over z all squared plus y over z all squared equals 1. So when we divide out, what we do see indeed is x over z squared plus y over z squared equals 1. Well, we also notice that x over z and y over z are rational numbers. They're fractions. So we find the pair of rational numbers xz and yz, and we find that that pair is a solution to the equation x squared plus y squared equals 1. Let me just take a second here. Don't want to interrupt things, but I'm going to use a capital X and a capital Y when talking about this equation x squared plus y squared equals 1, not to be confused with the lowercase xyz that corresponds to a Pythagorean triple. So it's a little bit unfortunate notation, but that's kind of the standard, and I'd like to stay with the standard. So what we see here is that a natural number solution to the Pythagorean equation leads to a rational number solution to the equation x squared plus y squared equals 1. So, for example, the Pythagorean triple 5, 12, 13 leads to the rational solution 5/13 comma 12/13 to the equation x squared plus y squared equals 1. And we can check this for ourselves. If we take 5/13 and square it, we see 25 over 169, and then we add to it 12/13 squared, which is 144, divided by 169. When we add those two together, happily we see 169 over 169, which in fact is 1. Well, if we consider the coordinate plane and plot the numbers x comma y that satisfy the equation x squared plus y squared equals 1, then we saw in the previous lecture that we obtain the graph of a circle centered at the origin 0, 0, and having radius 1. Now, it's easy to see, for example, that 1, 0 is a point on the circle because if you square 1 and add it to 0 squared, we get 1. So is negative 1 comma 0, as is 0 comma 1, and 0 comma negative 1. So we have 4 points on this graph, and they actually correspond to the locations, the north, south, east, and west. Well, from our previous observations, we also see that we can have other points. We could have a positive negative 3/5, comma positive negative 4/5. So there are 4 points right there that we could add to our graph, as we can positive negative 5/13, comma positive negative 12/13. And so we have 8 points more we can add on, and you can see that these points fit perfectly on the circle. So they correspond to points on the circle. Well, recall that the circle having radius 1 and centered at the origin 0, 0 is called the unit circle because the radius is 1 unit. In addition, we called a point on the circle a rational point if both coordinates are rational numbers. So 5/13, comma 12/13 is a rational point on the unit circle. Well, so we have that for each Pythagorean triple xyz, that in fact leads to a rational point on the unit circle, namely x over z, comma y over z. Now, this correspondence also holds in the other direction. In other words, rational points on the unit circle lead to Pythagorean triples. For example, the rational point 7/25, comma 24/25 is a rational point on the unit circle. And we can just verify that by taking 7/25 and squaring it and adding it to 24/25 squared. And we'd see 49 over 625 plus 576 over 625. We add them happily, we get 625 over 625, which is 1. It's a point on the circle. Well, this point corresponds to the Pythagorean triple 7, comma 24, comma 25. 7, 24, 25 is the Pythagorean triple. So we have a correspondence, or a dictionary, if you will, that lets us go back and forth between rational points on the unit circle and Pythagorean triples. Therefore, we can find all Pythagorean triples, and if we wanted to do that, to find them all, it's actually equivalent to finding all the rational points on the unit circle. So we find this correspondence. To find a solution to a certain Diophantine equation, we just find rational points on a unit circle. Well, now, circles are supremely symmetric, but that graceful curvature that they possess makes them at once subtle and complex. Thus, let's momentarily forego the subtle circle and consider the simplest graphs imaginable. These would be graphs that have no curvature at all, and we come upon the straight line. While the equation of the unit circle involves squares, x squared plus y squared equals 1, the equations for the straight lines that we're going to consider look like y equals 3 times x plus 1, or y equals negative 8 times x plus 1, or y equals 2/5 times x plus 1. Now, we notice that there are no squares appearing in these formulas, and that's why the graphs are straight lines rather than curves. We also observe that each of these lines shares a common point, namely x equals negative 1 and y equals 0, which we could write as the ordered pair negative 1, comma 0. And we can check this for ourselves. Let's let x equal negative 1 and see what y has to equal by replacing the x by negative 1 and seeing what y is. Well, y would equal 3 times x, which is now negative 1, so we have negative 1 plus 1. Negative 1 plus 1 is 0. 3 times 0 is 0, so happily y equals 0, as I claimed. Well, and this point, by the way, is shared for all the lines that we just looked at. Well, because a straight line is uniquely determined by knowing just 2 points, to graph a line, given its equation, we need only find 2 points, plot them, and then connect with a straight line. For example, if we consider the given line y equals 3 times x plus 1, we've already seen that it contains negative 1, comma 0. So if we let x be another point, let's say x equals 1, then we'd see that y equals 3 times 1 plus 1, which is 2, 3 times 2 is 6. And so we see another point is 1 comma 6, and that must be on the line. So if we plot those 2 points, connect them with the line, then we found the graph of that line. Similarly, if we consider the line given by y equals -8 times the quantity x plus 1, we again know that it contains -1 comma 0. And if we let x equal 1, then we can see that y equals -8 times 1 plus 1, which is 2. 2 times -8 is -16. And so we find another point, namely 1 comma -16, that's on the line. We plot those 2 points, connect them with a straight line, and we've just graphed that line. Finally, just for practice, if we consider the line given by y equals 2/5 times x plus 1, again, we know that it contains -1 comma 0. If we let x equal 1 to find another point, then we'd see that y equals 2/5 times 1 plus 1, which is 2. 2 times 2/5 is 4/5. And so we found a second point on the line, 1 comma 4/5. And if we connect those 2 points with a straight line, we see the line associated with this equation. Well, now, as we look at these different graphs of these 3 lines, we notice 2 features, and I want us to celebrate them right now. First, they all pass through the point -1 comma 0, which of course we already knew, but are now seeing visually. Secondly, we see that the number multiplying the x plus 1 term affects the pitch of the line. The larger the number, the more steep the line. The pitch of a line is called the slope, and it is precisely defined as the ratio of the change in the vertical direction to the change in the horizontal direction. And so informally, students remember slope as rise over run. Well, that ratio, the slope of a line, is usually in mathematics denoted by the lowercase letter m. The larger the m, the steeper the line is. Now, if m, or the slope, is positive, then the line is heading upward as it moves to the right. And if m, in fact, were to be a negative number, then the line is heading downward as it moves to the right. So given this notation, we can describe the particular type of lines that we'll be interested in a generic type of equation as y equals m times the quantity x plus 1. Notice that's the shape of all the lines we've looked at so far. Remember, m here represents the line's slope. Well, the key point for us is that these particular lines always pass through the point -1 comma 0, and that altering the m, or equivalently altering the slope, is as though we were altering the pitch. So in some sense, we can view these lines as being anchored at that point, -1, 0, and we're just pivoting along that point, and depending upon the slope, we see a particular line. Well, we're now ready to combine our 2 types of graphs, the circle with the lines. Now, if we consider the unit circle together with our straight lines that pass through the point -1 comma 0, then we see that these 2 graphs intersect at exactly 2 points. The known point, -1 comma 0, which is the westernmost point on the unit circle, and also the point at which the line crosses the x-axis, if you notice. And then they intersect at a second point. Now, the reason why there are 2 points of intersection is because the equation for the circle is quadratic. It has powers involving 2 and no larger powers. The exponent 2 is what yields the 2 solutions. And we'll return to this observation at the close of this lecture and in the next one as well. Now, however, our goal is to find that second point of intersection precisely in terms of the slope or the pitch of the line m. So we'll view the slope m as fixed, but at the moment unknown. So it's a fixed unknown number. Well, as we're what we're going to do now is, as we'll see after a minute of algebra, the second point of intersection will in fact lead us to the Pythagorean triple that we seek. So stay tuned. Okay, now we're going to do a little bit of algebra. So if you are not particularly drawn toward algebra, no problem. Sit back and enjoy the view of me doing it and be thrilled that there's no quiz. And if you happen to love algebra, then in fact, sit at the very edge of your seats because you're in for a lot of fun. Okay, so now it's time for some entertaining algebra. Okay, we're going to want to find that second point by solving the two equations, y equals m times x plus 1, and the circle x squared plus y squared equals 1 simultaneously. This is going to be a little bit tricky, but I'll do it for you. So we solve these equations by replacing the y in the formula for the circle by what it equals in the line equation. Namely, we know that y equals m times x plus 1. So after we substitute that in place of y in the circle, we see x squared plus, and instead of y squared, we see m times x plus 1, all squared equals 1. Now, if we expand and recombine all the terms, this actually becomes the following. The quantity 1 plus m squared times x squared plus 2m squared times x plus m squared minus 1 equals 0. I know it looks a little bit messy, but look, there's no y's. There's no y's. Well, the left-hand side, in fact, can be factored, and we've factored things before. This one's a little bit trickier, so I'll do it for us. It can be factored as the quantity x plus 1 times the factor quantity 1 plus m squared times x plus m squared minus 1. And those two factors, when multiplied, equal 0. Well, let's think about that. If we have the product of two numbers multiplying and equaling 0, there's only one possibility. Well, in fact, there's two possibilities. Either the first term is 0 or the second term is 0. Those are the only possibilities. So we have two solutions. Well, to find our two solutions, we see that either the first factor, x plus 1 equals 0, or the second factor, 1 plus m squared times x plus m squared minus 1 equals 0. Now, the first equation gives us that x equals negative 1, which is our original point of intersection, negative 1 comma 0. So we've learned nothing new. But of course, the equations didn't know that that was the point we knew. The equations and mathematics will spit out all the solutions. So even though we learned nothing new, it's always great to see that we haven't made a mathematical mistake. We get the right point. The second equation gives us the other point of intersection, which works out to be x equals 1 minus m squared, all divided by 1 plus m squared. Now, to find the corresponding y value for this x value, we insert the x value we just found back into the equation for the line, y equals m times x plus 1. And in this case, if we simplify, we would discover that y equals 2 times m, all divided by 1 plus m squared. Okay, great. Well, we survived most of the algebra. Fun. So, given any slope m, we found the 2 points of intersection of the line and the circle. One point is our known point, negative 1 comma 0, and the other point is the more exotic point, which has x value 1 minus m squared over 1 plus m squared, and a y value of 2m all over 1 plus m squared. Now, notice how this second point of intersection will in fact vary as we change m. Interesting. Okay, well, in this exercise, notice how we first used geometry to visualize the circle and lines and their points of intersection, and then applied algebra to find those points precisely by using the equations that described the graphs. Well, this powerful synergy between geometry and algebra is the basis for an important field of study known as algebraic geometry. In fact, as we'll see in the next lecture, the points of intersection of lines and curves play a central role in our understanding of certain Diophantine equations. So stay tuned. Well, returning to our work with the intersection of the circle and lines, we now see that given any slope m, we can find that second point of intersection of the unit circle and that given line. Now, I'm going to pick a special type of number for our slope m. I'm going to make sure that it's a rational number, so it's a fraction, that's smaller than 1. Now, to do this, let's select natural numbers a and b, where a is going to be larger than b, and let's consider the line having slope m, which will equal b over a. b over a. Now, since a is bigger than b, then b over a is a number less than 1. Now, remember that in the previous lecture, we used a and b as the parameters in describing the Pythagorean triples. So we're getting close to familiar terrain. So here we come. Well, given m as b over a, we can find the second point of intersection with the circle. We just replace all the m's by b over a's, and so that point would be, and this is going to be kind of like an algebraic tongue twister to say out loud, 1 minus the quantity b over a squared divided by 1 plus b over a all squared. That's the x value, and the y value will be 2 times b over a all divided by 1 plus b over a squared. That sounds kind of awful, but when you simplify it, it becomes, beautifully enough, a squared minus b squared all divided by a squared plus b squared. That's the x value. And the y value is 2ab all divided by a squared plus b squared. Notice how beautiful that point of intersection actually looks when written in terms of a and b. Okay, now, this point, okay, I admit, certainly is complicated looking. However, we know it's a rational point, and it's a point of intersection, so in fact, we know it's a rational point on the circle. That insight, together with the correspondence that we made earlier that connects rational points on circles to Pythagorean triples, implies that we have a Pythagorean triple. In this case, a squared minus b squared, 2ab, a squared plus b squared, which is exactly the formula we found in generating Pythagorean triples in the previous lecture. However, now we know that we found all the Pythagorean triples because every triple corresponds to a point of intersection with the unit circle and one of our lines. Thus, this combination of algebra and geometry allowed us to prove that we found every Pythagorean triple. Absolutely fantastic how these two come together. Well, let's close by stepping back and enjoying the big picture of what we've been exploring. Now, the circle, of course, is a very special curve. In fact, it's an example of what's called a conic section. Now, a conic section is any curve that can be realized by slicing an ice cream cone-like surface with a plane. Let's think about that for a second. So imagine an ice cream cone surface. If you have one, good for you. I happen to have one here. Of course, there's no ice cream in it, so that's a little bit sad. But the way mathematicians think about this is to actually put it on its head. And so it almost looks like a large, you can imagine like a dunce's cap kind of thing. So this is a cone, and we can actually now produce other geometric objects by taking the cone and now intersecting it with a plane, or if you will, a knife. And notice that if you were to just go right across and cut this right here, and pretending it won't crack, what we would get, of course, would be this, a perfect circle. And so there's our circle. So a circle is an example of a conic section, and more generally, conic sections are any sections we can get by taking an ice cream cone and slicing through with a plane. Now, there are other conic sections, and I wanted to share some of them with you. One which looks like a circle but isn't quite is called an ellipse. And that's formed by taking the ice cream cone and slicing with a plane that's not parallel to the floor, but instead a little bit skew. And you can see this beautiful curve, this beautiful oval, is in fact what's defined to be mathematically an ellipse. So this is, in fact, an ellipse. So that's another type of conic section. A circle, notice, is a special case of the ellipse. Now, another type of famous conic section that we've actually seen ourselves is called the parabola. This is where we take the conic section and we now slice, but we actually slice parallel to a side. So here's a side, and here's another side. And if we slice parallel, you see we get this wonderful shape. And that looks very much like the parabola graphs that we saw when we were kids. Then this is something that is, again, familiar, comes from the ice cream cone as well. All good things come from ice cream cones. Have you noticed that? And finally, the hyperbola, which looks very much like the parabola, but now we slice actually perpendicular to the floor. And so what we see here is a more dramatic curve compared to that of the parabola. Now, in fact, this is not quite right. So I have to admit that actually this is not quite right, because really, to do this correctly, to do this justice, we actually need two ice cream cones, and we put one on top of the other like this. So if you want to really see that for real, I actually do have two ice cream cones. And so technically you want this. Now notice what happens. If we were to actually slice this perpendicular to the floor, we would actually have two wings, wouldn't we? We would slice a bottom wing, and we would slice a top wing. And that's why the hyperbola has two wings, a top and a bottom, and they approach what are called asymptotes, which is not important here. The parabola, of course, does not have two wings, because if we slice parallel to the edge, then in fact we only hit either the lower or the higher one, but not both. We only hit both when we come down like this. And so that's why the hyperbola has two wings and the parabola has one. Well, each of these curves can be drawn in the coordinate plane, so that the points on a particular curve are solutions to a corresponding equation. And these equations are all quadratic, meaning that they all have exponents equal to 2. Thus, if we intersect any of these curves with a straight line, we'll again see that we have exactly 2 points of intersection. Well, in the next lecture, we'll consider equations that are even more complicated. They have an exponent of 3. They're cubic, and their graphs cannot simply be generated by slicing an ice cream cone with a plane. The subtle curves that we're about to study gracefully move number theory forward. These curves that we are about to see are known as elliptic curves. And they're the beautiful modern objects that not only move and drive number theory forward, but also will finally resolve the ancient tale of Fermat's last theorem.